type something in the chat so that we know. Okay, so our today's speaker is Dmitrii Ostrovskii from USD, and he's an expert on statistics of simulation. I enjoyed reading many of his papers, and today he's talking about efficient and near-optimal online portfolio selection. So it sounds like something in operations research, but I'm sure there's some interesting math there.
Right. Thanks, Jake. So first of all, yeah, I'm very grateful for every single paper. I don't know how many of them there are. I mean, I know not so many, but anyways, about the topic, first of all, this is a joint work with Rémi and also Pierre. So Rémi is wonderful. Like, consider him. I think he's going to industry now, but he's really a very, very good student. So, okay, so what this is about, this is online portfolio selection, but don't be bored. It's really online optimization. And in fact, despite it being online optimization, I will not talk, like more than half of the talk today I will spend talking about variational approximations, and like it really doesn't have to do much with online optimization. So first of all, very rough outline. So the first part of the talk will actually be on online optimization and portfolio selection, right? And essentially, we will introduce what can be considered state of the art since the early 2000s. So where's the pointer? Oh yeah, it works. Which is this algorithm called universal portfolios. Okay, then I will introduce what our approach is and how does it compare with this one, and why this is, where is the progress here really. And then, check, are we still online?
My bad. Okay. I just thought I can also join.
Okay. Can we just check that I'm still online?
Can you maybe scroll and I'll see it here.
Okay.
Yeah, I think you're still
okay. And can you hear? Can anybody hear anything? Like if you put me hello.
I don't know if no one complains. That's just
okay. So just like, yeah. Okay. So they now can see. Now we see that they can see. Okay. So basically, then there's going to be a technical part, and this technical part. So you see this thing in white in gray is something I will not be talking about because it's a stochastic seminar. So you might not be that interested in this, and instead I will be spending time talking about this stuff. Okay. So the goal will be to have, in some sense, rigorous derivation of this from that, like this as an approximate version of that. Okay, so this is an inside joke, but yeah. So yeah, the joke about this thing is that now we're all going to be rich. So that's what my authors are making a joke, and like other people. Anyway, so now talk about the problem first of all. So let me introduce the problem really. Online portfolio selection. This is a formulation due to Tom Cover in '91. He introduced the problem and also introduced the algorithm called universal portfolios to solve it ultimately in a way. So the problem is this. Okay, so you play as a trader, you play against the nature, the market. The market is adversarial, who wants to punish you because essentially it's other people want to get rich in your state. So now you start with initial capital, unit capital. And then for time, like let's say the time horizon, the overall time horizon is known, big T. What happens is that at each moment T, discrete time, you select a distribution or a point on the simplex WT called a portfolio, which is a way to, okay, so simplex is in dimension D, so it's D outcomes. So it's basically this vector tells you how you distribute your capital at the current time T over D assets, whatever these assets are. Now, as soon as you made this choice, okay, so the market sees it and chooses the XT. So it's essentially relative prices. So it's how much the ratios. That's why the vector has all the entries of the vector are positive ordered. So essentially, how much it's the ratio of the new price of each asset to the old price. Okay. Okay, so because it's the ratio, that means that if you look at this guy is simply how much is the ratio of how your capital increases, right? So then what happens is that after this round, so XT now you actually know XT, but only after the market punished you. Okay, so in a way, paid you, if you will, by increasing your capital at the time t minus 1, the previous one. So the new one is the previous one times this guy, times this ratio, and it keeps on going like this. Okay, so in a way, this is probably simplest possible adversarial model of like playing in a market. So okay, now money compounds multiplicatively, and market plays against you. These are the two main ideas. Now, our goal is to choose a sequence of portfolios, W1 to W capital T, that will guarantee us large finite capital T, which is, of course, the product of these guys. Okay. So the point is that each WT can depend on only on the previous x1 through xt minus 1. And so it goes. Okay. Now, of course, I want to make it convex optimization. That's why, like convex optimization, that's why what I do is I say, okay, so I have my loss function, which is this LTW at time t, which is simply minus log of this guy. Now it becomes the loss because the log is minus log is decreasing function. All right. So, and I'm in a kind of more, kind of, let's say, Eastern European mindset where I'm losing instead of gaining. Anyway, so now I'm maximizing. So maximizing capital big T means minimizing the final cumulative loss, which is a minus log of capital big T, which is the sum of the losses LT. I'm intent on not saying exactly what it means maximizing, because it will be in the next slide. Now, okay, so baseline, what we compare with, because I want it to be online convex optimization, I want to compare it with a single best static selection of the portfolio. Okay, so that means that my regret, which I will denote RT for the sequence W1 through big T, this notation means if the market the observed sequence of market states was this, so the sequence of return vectors was this, so the regret is simply the sum of the losses that I actually paid minus the minimum possible cumulative loss, but on a static strategy, so on a single portfolio. That is the same. Now there is some motivation from the point of view of trading why this kind of makes sense, despite kind of not really making much sense if you start thinking about it. I will not go into details. I don't want to spend time on it. Suffice to say that this is, from the point of view of online convex optimization, this is a standard setup. Also, there is even some motivation why it would also work not so bad for trading. And finally, so yeah, basically, finally, a very short remark. It's like it's proved in one line that the regret cannot be, in some sense, can only be very bad, can only be like linear, growing linear in big T if you compare against the best dynamic strategy. So the best sequence of portfolio. So in that problem, you really cannot do anything. That's kind of another motivation. So okay, so long story short, this is our regret. Our goal is to guarantee small regret uniformly over all possible markets. This is why universal in the name of covers paper 91 and his algorithm, because it's universally over the market. Whatever the market is, it's completely adversarial. You don't think about any distribution behind. But for any sequence here, you manage to guarantee that the regret is small. So I will not use this notation later on, but basically I want to say that it's sublinear in T. First of all, this is kind of one thing to solve the problem. Like, if it's not sublinear in T, then it's just like it's completely unsatisfactory. We're not talking about.
I have a very naive question.
Yes.
So in principle, this regret can even be negative if.
That's a good question. Yeah, in principle, it can be negative. In this problem, well, first of all, in this problem, it cannot be as it turns out because there are lower bounds that actually are attained. But in principle, there is some directional restriction. Negative regret. Honestly, in this one, I'm not an expert, but yeah. By the way, lower bound here, in my view, wasn't so easy to prove. Anyway, so Carl's algorithm now. Tom Covers, so he introduced this model, and he said, okay, so I know how to solve it in a way which turned out to be optimal later on, like optimal up to a constant factor. So before explaining his approach, let's start with a naive approach, which will not work. Okay, but kind of suggests some reasonable intuition. So let's start with the algorithm called follow the leader, right? Where we say, okay, there should be WT, I'm sorry, WT here, not WT plus 1. So the portfolio at each round, so I mean, we kind of want in the end to minimize the total, the final cumulative loss. So let's minimize instead of each round the part of it that we observed so far. This is also called fictitious play. And then, so I mean, as reasonable as it seems to be, in fact, it doesn't quite work. I mean, you can really like improve something until you will regret. Well, definitely it's not optimal, and it's maybe you can prove like square root to regret. Anyway, so the point is that this is not what we were going to do, and this is not what covered it. What he did instead, he said, okay, oh yeah, by the way, I already worked it out. Sorry. So yeah, so essentially it's not stable enough. Okay, so this is one explanation. So regret can be linear for this strategy. Essentially, if your market just kind of like plays you with you like this 0 1 0 1, like one asset, it puts like everything on one asset, the other one, the other, even in 2D you can prove that stuff. Okay, so the regret is linear. Now, key trick is then to robustify the procedure. And instead of playing the minimum of the cumulative loss, what you do is that, okay, so I can consider distribution that I will denote this way. So the density, which is exponential minus cumulative loss, the currently observed cumulative loss, all this like on the simplex. So in fact, like this thing has a normalization constant, which is the integral here. So I divide over the integral over the simplex of this thing. Okay, so and then so what I will do is that I will actually play the average over this distribution. So I can write the integral here, it's the actual average. There is no statistics here so far. It's the population, it's the averaging over some density on the simplex. Okay, so what, in other words, what it actually says is that for each W, you assign the weight proportional to the amount of money you would have earned, right? Because it's exponential minus sum of logs. It's actually the capital, current capital here, right? Minus sum of minus logs, right? So it's like really the exponential of the log, of the overall log of the product so far. So in other words, what you do is that you put like at any portfolio, you just look, oh, okay, so how much it would gain by now, okay, and then you put to it weight proportional to this amount. That's really what you do. Now, it turns out it works. So in particular, you can prove this. So the regret toward d minus 1. So d minus 1, you know, just like I will comment once again, just one time, why it's like really d minus 1. It's d minus 1 because for DSS, the simplex has a prime dimension d minus 1 and not d. And in fact, the bounds, the log factor should come out with d minus 1. But okay, so long story short, d minus 1 times log of something depending on t. So log of t. This is your regret. So it almost doesn't depend on big T. So it's like nearly constant in a way. It linearly depends on z. And very importantly, it doesn't like really here. Well, okay, so there is constant 1 here, and the lower bound has a smaller constant, perhaps a bit. But the point is that this is really, this constant 1 here is a numerical constant. So there is no dependence on the ranges. You don't restrict the ranges of the returns in no way. Okay? So, and now, okay, so some story about it. Well, first of all, I mean, this is an improvable up to a constant factor. Every time in this talk, when I say near optimal, you know, it's basically near stands for the constant, which I don't care about. It's not sharp up to a constant. And actually, also sometimes the log of t will be replaced with log of t plus d, but you will forgive me this. Now, okay, so computationally, the problem with this, okay, so the thing is that it's super nice from the point of view of regret. The problem is that it's computationally prohibitive. And because why is that? Well, because we integrate over some density in RD. So okay, so you say, okay, my density is log concave, so I can sample from it at least, and then I can try to approximate this expectation by sampling. And then if I apply a lot of the whole science how to sample properly from log concave density, I can get some polynomial implementations of this thing. The problem with that, it will not be fast. Okay, so essentially, this is what Gaillard and Impala did in the early 2000s. This is what the runtime per round, so per update, that they figured out. You can slightly improve it, but the point is that you will not expect here anything like with really like this 14. Like there might be ways to make it less than 10, but it's not like square even. Okay, and now open problem. So really, like this was the time. In some sense, improvements, like strict improvements, there were no improvements over this result. So I will comment what kind of improvements, not improvements, but what kind of progress there were in the next slide. But first, open problem. So propose a regret optimal, near optimal algorithm that can be also, let's say, practical, or let's say really computationally feasible. Like I really don't want this D4 T plus D14 here. I want something reasonable. But like what reasonable, again, we will see later on. Now, just very brief history. So, D log T is the right regret proposed proved by Cover. His proof is actually non-asymptotical, although he writes it asymptotic. Anyway, now Gaillard and Impala do essentially his algorithm, but with approximation of sampling by sampling with like this runtime. So I kind of hide T plus D. So let's say T is bigger than D, and then I will just hide D just to make the formulas more compact. Then what happened is that people said, okay, we don't know how to make optimal regret faster. Let's just try to do something but fast. Okay, and this is okay. So they first applied the version of gradient descent, exponentiated gradient, because it's a line learning problem, right? Exponentiated gradient allows you to kind of to save on the norm of the gradients because it's the right geometry for the simplex. Right, then there was like really nice online Newton step by Hazan and his co-authors Garval. So they said, okay, so we know how to do kind of like D log T, except that now there is this G thing, and this G is a norm of the gradient. Actually, it's G infinity, the L infinity norm of the gradients. They write it as L2, but never mind. So it's actually L infinity. But the point is that this is actually a strong assumption. If you will, like this assumption corresponds to you're not allowing the return ratios. Like return ratios should be bounded from below and from above by a constant. It's a very strong assumption. So okay, but the point about this is that all of this is fast. Okay, so online Newton step is slower, but actually, by the way, this is not the right result for them. There is also price of projection, and here you have to solve a quadratic problem. But anyway, our goal is not to show that this is great. So the point is that all these approaches are fast. The first two of them had sublinear regret, but not the near constant regret in T. Then there was this improvement with constant regret in T, but still dependence on G. Then dependence on G was eliminated in some approach with dependence on T still in place. Then there was actually a really good work 3 years ago by Hepeglu. We figured out a really complicated way to make it work with really some reasonable runtime and regret, which is optimal except for D squared instead of D. And then there was really the problem here. People tried it hard, and several groups. There are 2 who published, and there are several others who did not. So, but they were working on that. So the point is that you can kind of tweak his algorithm, which is already complicated. You can really work very hard, introduce some more tricks, and kind of make it the runtime. You can make it not dependent on T, which is kind of what we want to do because it's in each round. So we don't want the runtime of the round to grow with T. But the D square is really, it sits there. So It's like d squared is kind of, it's lost somewhere in that algorithm. At this point right now, I don't remember. At some point I read his paper line by line, so and it was kind of clear where the problems were, but now we can instead look at the optimal approach. Anyway, so the result is this. The runtime is d squared t plus d. We tried to make it d cube. Tried reasonably hard, we could not. But maybe we just didn't try hard enough. So now let me explain the main ideas. So before I will explain the algorithm itself, let me introduce another one, like a simpler one, which does not give the right regret, but it's kind of one step closer. So I say, okay, so I need some stability in the choice of my portfolios. So what I will do is that I will add to the cumulative loss, I will add the logarithmic barrier on the simplex, which will at least kind of not like prohibit me from coming too close to the boundaries of the simplex. So it will kind of like force me to be closer to the uniform portfolio. I don't say uniform distributions on purpose, but just like the point that puts equal sum of money for each asset. In other words, by the way, this can also be viewed as just saying that, well, in fact, in the beginning, I observed D like fictitious asset returns. So there were like D fictitious rounds where like they would just show me like a single record. Right? And this, let's call it LBFTRL. So follow the regularized leader with logarithmic barrier. Okay, so there was an open call like three years ago, or 2 years ago, which kind of made all the folks work on this paper. The community, they said, okay, so maybe we can, maybe we can prove that actually this has the right regret. Okay, so they looked at it, but it turned out that the problems they had there, they are unsurmountable. So here's what they did. So first of all, these guys in the node team, Van Aaron and others, so they said, okay, we know how to do slow regret or like large regret, square root of dt, which would correspond to choosing this regularization parameter growing in T somehow, which doesn't seem to be a right thing to do. But anyway, so they said, okay, we can do this, and we conjecture that you can do the optimal regret, but unfortunately, actually, you can't. So in one of these two papers, in this one, there was a lower bound saying that this is not possible. So I will not stop on this result much more, but essentially you will not get any polynomial regret in Z or large enough T. Now, and then like we're thinking how to correct this, and here's how, as it turns out, how you can correct this. So you need to add something else. You need to add some regularizer that depends on T. The fact that the regularizer should depend on T was kind of clear to all folks who were working on this. The question was which regularizer really. Okay. Then, as it turns out, so if you add up the volumetric barrier regularizer, which is this function, I will explain in a second what is this function really. Then what happens is that essentially it will work with the right regret, while at the same time you will preserve the computational tractability. So first of all, let's go back to this guy. Why this is computationally tractable? Well, it's a convex function, which is, so this is a convex function, right? Which is in fact, you can prove that is what is called self-concordant. Without stopping on self-concordance, we will go over it in a few slides when things will get technical. But long story short, it's a function on which you know that you can run Newton's method, and you will have very, very favorable convergence guarantees for the Newton method. And then, as it turns out, this self-concordance property is preserved when you add up this guy here, which is, by the way, not a trivial fact at all. But like through some pretty tedious calculations, you can actually check it. And this was done. I would say this was probably the main technical step in Weiz's paper in the 1890s. Okay. Well, first of all, it's really, let's kind of try to convince ourselves why this thing is convex, which is okay. So first of all, what this thing is, you take VT. Let me define VT of W as this. So I take the Hessian of LT of W, right? The Hessian of LT of W. So LT is the sum of logs, right? So the Hessian will be the sum of one rank guys, one rank matrices, where the one rank terms are their dependence on W is inverse quadratic. So you can divide over squares of WTs. Well, because of this, you can kind of look at this as kind of like minus log with some factors of WTs. But this is why n of it. It should be convex, but this is of course not a rigorous argument. Okay, so at least I can kind of manage you at some level and formally convince that this thing would be computationally tractable. In fact, this fact, the implementation of this, it's in the paper. I will not talk about it today, but in fact, there is a way to just make it work with Newton's method by using like logarithmic number of steps. So you will have linearly convergent variant of Newton's method because it's like actually a quasi-Newton's method because you will have to approximate the Hessian, but I will not talk about it today. So what I will talk. Another thing I will not talk about today is why this thing has optimal regret from the first place, and how this thing was figured out. So essentially, there is like a way of looking at it as okay. So this regularizer is something that precisely cures the problem that Van Erden and others met in their suggestion. Then there is a way to just to kind of to prove it that there will be the right regret. So instead, what I will want to do in the remaining time is that I want to convince you that in fact this arises as some sort of approximation of universal portfolios, where I can even say that this approximation is reasonable in some rigorous way. But then if I know that universal portfolios is optimal, that gives me hope that this thing will also be regret optimal. I'm not saying it's proof, like it doesn't follow from this approximation argument I'm about to give that the regret is optimal. But I'm not talking about the regret proof today. My goal is to convince you, because it's a stochastic seminar, and this part is stochastic, how this thing relates to universal portfolios. So let's talk about this thing instead. Now, but first of all, I will formulate the result, however. So the result we have is this. So first of all, so if I define the hybrid, if I define the hybrid barrier, so this PT, P stands for potential that we minimize at each step, as the cumulative loss plus a volumetric barrier with some regularizer mu, right? This guy from the previous slide is 1/2 of the log determinant of the Hessian of LT. Then this is the algorithm, really. It turns out that it's near optimal. So here's the result, the regret. So there is like this simplified result, but the message is that for lambda and mu bigger than some constants, and with certain relations between them satisfied, in particular, you can take this pair of constants and it will work. The sequence of portfolios that you produce has regret optimal up to a replacement of log t with log t plus of d, and a constant, different constant. Now, this is the result. I will not comment more on tractability, but now let's try to discuss this connection. So technical part of the talk now. Maybe it's the right time to answer some questions if there are any. From this part, I will have to process math, so it will be like some pauses. Okay, I will move on. So now, really, so our goal is that okay. So let's say you are, for some reason, you believe that universal portfolios work. In fact, you can consider generalized version of universal portfolios, where instead of factor 1 here, you put 1 over mu. So mu is your kind of your temperature parameter. And temperature cannot be too small, cannot be too close to absolute zero, because absolute zero corresponds to follow the leader, which it doesn't work. So the first step is, which I'm kind of omitting here, but it's kind of done with more or less standard ways, is just to extend to say, okay, so actually if mu is bigger than some constant, then this algorithm is still optimal with any such. But regret, with additional regret, depending on mu. So regret will grow when mu grows, but that's fine. Because like as soon as mu is a constant, the regret is still a constant. Constant times zero. So another fact that we will use is this. So okay, so let me call this guy, so universal portfolios is this distribution of the portfolios, this density. We say density to avoid ambiguity. So density means a distribution over the simplex. It's distribution over possible portfolios. So I have Gibbs duality, right? So I have that exponential distribution with like exponential of some function. I can write it down as a solution of some rational problem, where what I do is that I define linear functional. So this thing will be, so this with calligraphic capitals, I will denote functionals of distributions. This square brackets. Check, you're talking right now. That's what Zoom shows me.
Yeah.
Okay. So yeah, probably if you mute it, they will understand. But anyway, so let me denote that this like soup of some subset of the simplex is a set of all distributions supported on the set. Right? So like soup of delta D is the set of all distributions supported on the simplex. And then I define as functional. So my functional phi is for any phi, any such distribution and density. It's a I take expectation or distribution of LT. LT. Okay. So another thing which I did not mention here is that I'm also not convincing you that if I actually add up the logarithmic barrier here, then it will still not hurt the performance of Cover's algorithm. So in fact, you can kind of start up thinking that here, instead of just this sum, there is also the logarithmic barrier. As soon as lambda is a constant, it will work. It's kind of reasonable because we know that logarithmic barrier, like it shouldn't hurt you. But now, okay, so I say that if I have this expectation of L and I have H, so H is the differential entropy of my density. Then in fact, I have this. So differential entropy is just the expectation of the minus log over the density. Minus log of the density over the density. It's in this version of it. Now, in fact, it's a well-known fact that ft, so phi t will minimize this function. It's previous time t minus 1. The point is that if I want to minimize this functional, which is linear function of minus entropy of the distribution, the result will be the exponential density of this minus linear function. Very well-known thing. And in fact, what is not written here is that I also have Fenkel-Legendre duality, right? Which I will call Gibbs duality in this context, which will tell me that phi, this f calligraphic of my phi, of the right phi, the optimal phi, will be the log partition function. Minus mu log partition function, but never mind, we're not using it right now yet. Now, mu is the temperature parameter. That means that increasing mu leads you from the leader, from a distribution that wants to concentrate on the leader. Leader is, by the way, always the mode of distribution, right? To a uniform density, right? And lambda, which is contained here inside L, which is not written here, but really, which is meant here. So lambda, increasing lambda biases you towards, biases the leader, so the mode of the distribution, towards the trivial portfolio, like the one that just splits equal. Okay. Anyway, now, by the way, how much time do I have overall?
You have like 15 minutes.
15 minutes will begin. So, okay, so optimization viewpoint is this. So now what I want to do is that now I want to somehow to massage this variational problem so that in the end I will get universal portfolios. So that's my plan for this remaining 15 minutes. And kind of thus convincing you that like this thing, the new algorithm, which is by the way called VB of TRL, can be thought of as an approximation of universal portfolios. In fact, this will be a rigorous statement because we will characterize the accuracy of this approximation. Okay. So before I formulate the result, so let me say, okay, so I work with this variational problem, which is in fact a convex optimization problem over distributions, right? Right. Clearly, this is a convex set of distributions. Right. Two distributions are supported on a simplex, the mixture is supported on a simplex. Now the problem, you can think about our problems here is that because it's an infinite dimensional, although this problem is a convex optimization problem, it's infinite dimensional one. That's why, in some sense, it's really not that tractable in a way. I mean, we have explicit formula for its solution, but we cannot even evaluate a linear function corresponding to expectation over this density. Now, and so instead, so what we will do is that we will approximate this rational problem. So by replacing the functional here and the constraint set here with something else. Okay, so what we will do is that, and why this we will get away with this? Well, essentially because we have that LT sum of logs, and logs are logarithms is a self-concordant function. And in a nutshell, self-concordant functions are those for which you have you can characterize how precise are local quadratic approximations. Now, okay. So here's a very, very rough outline of what we are about to do now. First of all, I will show how, what it means to replace LT with this local quadratic approximation. Next, we will argue by self-concordance that this approximation, so this approximation will work in a local set called Deakin ellipsoid. All this will be introduced next. So this is basically just for extras. And then we will focus on densities only supported in this ellipsoid. So effectively, what we will do is that we will replace F with its quadratic approximation, and we will replace the set of all densities supported on the simplex with the densities supported only on the Deakin ellipsoid around their expectation. And then we will see somehow, if time is enough, why this works and in what sense it works. Okay. And by the way, now, and this will be the part that I will show. So it works if I replace here F with this quadratic approximation and the support constraint with a Deakin ellipsoid support constraint. But what I will not show today, but what kind of is an easy part, is to say now if you have a density supported on an ellipsoid, right? And then you have to minimize the functional including entropy over this density. What will you have essentially is that because it's a quadratic approximation of phi, you will have a covariance term. So we'll have dependence on the expectation of this density inside this guy. Then you will have covariance term, so quadratic term depending on the covariance, and then you have entropy. But this is minimization over density supported now on the ellipsoid. Well, you see covariance, entropy, and ellipsoid together. So you want to do Gaussian approximation, Gaussian with covariance corresponding to this ellipsoid, essentially. But then for Gaussian, I know that entropy is maximized, right? Entropy of a Gaussian, I know that it's actually maximized on a Gaussian. That's why this thing works, by the way. That's why Gaussian is the right distribution with fixed expectation and covariance. But now you also know the entropy of this maximal entropy of a Gaussian. And so what you are left with optimization problem with actually known entropy that has a closed form expression of the mean and covariance. And what you have to now to minimize over is just mean and covariance. So now you have parametric optimization problem. And then as it turns out, you can solve for covariance with fixed mean and you will recover that out of it. So very short explanation is that the logarithmic beta arises as the entropy, well, not the entropy, but let's say that from the entropy of the Gaussian distribution. But okay, so now what I will want to do now is that I want to argue that this approximation here, outlined here, works. So to do this, okay. So to do this, so first of all, let me define the objects I was separating so far, right? When hand waving. So first of all, so formally, I do need to restrain myself to a fine subspace, which is a fine span of the simplex. So let me call it AD. And when I say ellipsoids, they're actually ellipsoids in this fine subspace. In fact, they have dimension deficient by 1. Just a small point so that we don't have questions. Now, Deakin ellipsoid. So here's the definition. Deakin ellipsoid of function LT. Ellipsoids are always be of this function LT. And LT, I just remind you, it's a cumulative loss plus the logarithmic beta, plus the lambda thing. Of radius R centered at some W hat, is this guy. So it's an ellipsoid centered really at W hat of radius R in the matrix generated by my Hessian. So this is a standard notation for Mohlanovis distance. So this means that it's the standard delta norm, but with square root of this matrix here. So in other words, you look, given a function, you look at your Hessian, so your function should be strictly convex, begin with, which this thing is. So you look, you compute the Hessian at this point, at the point where you stand, W hat. You look at the local, you look at the R radius ball in the corresponding matrix. So yes, Euclidean norm actually. Now, the point is that what we know, there are, like, the thing is that we know nice things about these ellipsoids for self-concordant functions. So first of all, what is self-concordant functions? It's really not that important in this talk, but let me say it's the functions for the right bound of the third derivative. So the third derivative is bounded in the right way in terms of the second derivative, which kind of allows you to control how fast the second derivative changes. And then it turns out that the definition of self-concordant is kind of like precisely the right definition for this control to be like well behaved. Now, what I'm interested in actually using some of the properties. So what I know is this: I actually have control of the second order Taylor expansion. So what is written here is that my function L self-concordant. So if I look at any point W hat, then L of W minus, so the error of the first order Taylor, so actually the error of the second order Taylor expansion, because if you subtract 1/2 of the quadratic guy here, this is the second order Taylor term. So the error of the second order Taylor expansion is controlled in terms of the quadratic error, the second order Taylor. So if I subtract 1/2 here, I will have something like 1/5, or like something, well, something smaller than 1 here, and minus this thing here. Now, as it turns out, so this is one thing we have. Another thing is that, well, actually, which is not written here, but I just want you to believe me on this. We'll use it a bit later. Is that actually ellipsoids, if you move inside an ellipsoid of some radius smaller than 1, then in a way the shape of the ellipsoids in these centers is preserved. So they kind of they get like shaken a bit, they get deformed, but not by much. There is a way to make it precise. In some sense, Hessian remains the same up to a constant factor inside the Jézéquel. Now, if you take expectation of this guy here, of this inequality, this is what you will recover. Our linear functional, right, L, which was the expectation of LT over W over your density. Turns out that you can look, so now it has like expansion where the first term is just L at the expectation, which is what you kind of expect to do. It's like LT of the portfolio that you choose. So this is kind of what you try to catch here, to catch the volumetric barrier regularization. Plus something, and this something depends on the covariance of the distribution norm. So it's like the trace of the covariance. So it's the inner product between the covariance and the Hessian at W hat. Believe me on this, is really just you take this expectation, this is what you will get. But because this term went away, right? Because W hat itself is the expectation. So the first order term went away. It's like a 0 order term plus the second. And you end up at the second because you have self-concordance. Now, so this suggests to do, okay, so let me call this guy the upper bound on the linear function. And this is the lower bound. So the L upper hat and like L upper bar and L lower bar. And so I know that if I'm like at W hat, then for all distributions supported on the Deakin ellipsoid of radius smaller than 1 around this W hat, as such that the expectation is the W hat, I have this thing. So for all such distributions supported on the Deakin ellipsoid around their expectation, I in fact have that LT is approximated from above and below with this simple thing, like LT of W hat plus a quadratic, plus this thing depending on the covariance and this. Now, be a bit faster. So now that suggests to replace my initial problem with this problem. So I take upper approximation, so I just leave entropy as it was before. Now I approximate LT with the upper bound on LT, and I zoom in into the distribution supported on a Deakin ellipsoid with unknown mean. So the mean is now what I'm allowed to vary to choose my distribution. But now the constraints are local. The distribution for any possible mean should be supported on a Deakin ellipsoid of some smaller, now for some technical reasons, I need some radius even smaller than 1/2, but this is not really important. So now what happened is that if I have distribution that minimizes, that solves this optimization problem, right? And the value of this problem can only be bigger than the previous one. In this sense, it's a relaxation. Let's not argue what a relaxation is, but let's call it approximation. Why? I mean, because we narrowed down the set, the constraint set, and we increase the value of the objective. So the minimum can only increase because now. So let's now formulate the result that I actually want to kind of very briefly show how, sketch very briefly how you can hope to prove it. So let me call, now from now on, I really suppress the dependence on T, like everything is done with a fixed T. Okay, and I just suppress the index, just like to ease the notation. And then what I want to show is this result. So in fact, this is my functional. I know that phi star, which is Cover's distribution, universal portfolio's distribution, minimizes the functional. I will call this guy the functional. Okay, the functional f over all distributions supported on the simplex. Now instead, I have phi bar, the upper guy. Now the upper distribution minimizes the upper bound of that functional, this guy, over smaller sets, or over all distributions that whatever is their mean on the simplex, they're supported on a Deakin ellipsoid around their mean. By the way, what I did not comment is that another property of self-concordant functions, which you usually prove first, the most important one, is that if you have a function which is self-concordant in some domain, then in fact Deakin ellipsoid of radius smaller than 1 is always inside your domain. So if you started with a point at your domain, and you draw around a Deakin ellipsoid with radius at most 1, the ellipsoids are not closed. Then this ellipsoid will be inside your domain. But why is that? Essentially, well, because from self-concordance, the first thing you prove is that actually the function should explode on the boundary, because it's the Hessian explodes on the boundary.
Why is that relevant to this slide?
Oh, into this line, because I want to claim that I'm inside in the simplex. Right, which is not doesn't follow from here. I allow to vary the expectation to vary over the simplex, right? But the distribution is supported on a Deakin ellipsoid around that expectation. If I don't know that the Deakin ellipsoid is instead inside of the domain, which is the simplex, because inside of this thing there is a self-concordant barrier for the simplex.
Well, you have the constraint that it's in the domain, so that's why
I have it here, but not here.
Well, you have W hat has to be inside. Oh, I see.
Yes, not enough.
I see.
It's not enough before like this remark. It is enough, or actually because I happen to know that Deakin ellipsoids. So if I take a point inside the domain, then the Deakin ellipsoid around that point will also be inside it. This is why it's. Am I clear?
Yeah.
Okay. Now, so what we want to prove is this. So if the thing is that this will not too much hurt us. This will not too much increase our functional if we focus only on these distributions up to a term which is of the order of the regret that we want to choose. So why this is a nice result? Well, because if this was not true, then there will be no hope. So this is the potential you minimize. If you minimize it up to the accuracy of the regret at which you aim, it's not enough to guarantee that the regret is small. And I don't know how to derive regret proof just from this. On the other hand, if this was not whole, if this would not be true, right? So in other words, if here the term will be bigger than the regret, then I don't see any hope why this would work. It's just like the approximation error at each step is too large. Anyway, now, so how we will prove it? So we'll prove precisely this inequality. So first of all, that at the upper distribution, f is smaller than the upper distribution than the f bar at phi bar. Oh,
So we have another seminar in 5 minutes.
Okay.
And in 2 minutes.
Okay, so I will be really quick then. So then it's like really a small time constraint. So the climax, for the climax to arrive, I will kind of like have to really compress this thing. So long story short, what you do is the first inequality here is trivial because f phi bar lives on the ellipsoid where f is approximated by f bar. And now you work with this. So now you want to prove that this thing, so the upper function at the upper distribution, is at most what you want it to be. But now, okay. The problem is that you want to go from the upper function to the usual function, right? Another problem is that you want to go from the solution that lives on ellipsoid to all possible minimizers over the whole set. So there are kind of two problems to solve. So showing how the first problem is solved, or essentially the trick, which kind of like a small technical trick here, is this. So essentially you consider now the lower approximation on a twice large ellipsoid. That's why I had to kind of start with 1/4. So now I consider 1/2, 1/2. And I say, okay, so the lower solution, so it minimizes on a slightly larger ellipsoid around its expectation, minimizes the lower function, right? But the thing is that now I can just squeeze this density, let me call the lower plus, is the density which is like, I kind of just squeeze the noise twice. Okay, so this is what I did. I just like preserve the expectation, W lower bar, or phi lower bar. And like everything else, I kind of squeeze it twice, closer to the expectation. So if I do this, then my new thing will leave. So this new distribution will leave on the ellipsoid of twice smaller radius. First of all, the expectation does not change because I squeeze the noise. And then I actually have that this new thing is feasible for the upper problem. It's feasible for the upper problem, but I also know that nothing in the function will change too much because I did not change my distribution too much. That's long story short. This allows me to prove this inequality that the upper function at the upper thing is at most, well, now I will use the feasibility of the phi bar plus into this problem. And I will also essentially know what is the covariance of phi of the squeeze distribution, squeeze lower distribution compared to the initial covariance. So now from this, it's kind of like more or less just keep doing these things. And then in the end, this kind of trick allows you, in a nutshell, to get rid of the approximation of the objective. But then there's still approximation by restricting the distribution to the Deakin ellipsoid instead of the whole simplex. To do this, it's more or less a direct calculation. So now what you use is you use Gibbs duality. And then so you said, okay, you say that similarly as the covers distribution is expressed, the value of the function of this distribution is expressed as a log partition function. Now, if we truncate this distribution to a Deakin ellipsoid, you also have a log partition function representation, except that now the integral is over a smaller domain. The truncated distribution is feasible. And again, by feasibility, you would have the bound that you want to prove. So you will replace this minimum by this guy. Okay, but now, except that now you have to track how much this truncation changes your function. Essentially, the changes in the entropy, the relevant change. This truncation can only decrease the covariance, but the entropy, the point is that it will not decrease the entropy too much. Proving this is more or less a direct calculation. So it's like knowing what is the volume of the simplex, knowing what is, the volume of the sphere, and just computing these things, more or less. It's kind of written here. And so let me just briefly comment on open questions. So first of all, what the message of this talk was, I kind of convinced you. So there is the new algorithm which has optimal regret. I did not explain really in detail technically why. I did not show you the regret proof, but I kind of gave like a circular argument why you would expect it to be optimal by connecting this guy to the classic algorithm for which the regret is not to be optimal. Now, What are the challenges? Just briefly, like 1 minute to comment. Or should I stop here? Maybe questions.
Yeah, I heard the room is reserved for 3,
Yeah.
right? So maybe,
Yeah.
yeah, that's, yeah.
Again, I
let's
pretty
thank-
much summarize the message, so yes.
Okay, so let's thank Dmitrii and we will leave the questions offline. Okay. Thank you. Yeah. Thanks.
Again, I have to go to a meeting right now with a doctor on my phone, but are you around for the rest?
Depends on what.
Oh. Hi.
Yeah,
How are you?
yeah, so we are going to dinner at maybe
That's the
6:30.
thing, yeah, so that
before that,
always an option. 7
Yeah.
p.m.
Can I just, can I, I'll send you a message in the next half an hour or so.
Okay.
Maybe we'll figure out.
Okay.
Yes, so let me.
yeah, I think he will be in this building, so.
Okay.
Yeah, maybe
Good,
we can
good.
talk to you, yeah.
Sorry that I have to run my doctor appointment right now on my phone.
Let us see.
Yeah, no problem. Okay.
Yeah, I have to squeeze this down the last one.
I agree. We should also want to. We do that.
Рабочая.